Okay, today's lecture is the last lecture on functions. As promised, we saved the best for last, so these are the special functions. Those of the increasing or decreasing kind, not very exciting, but we are going to learn something called piecewise functions as well as periodic functions. And you will find that these two are often intertwined in a question. Besides that, as a bonus, I'm going to share with you some useful GC keystrokes. Go through one of your self-reading examples in the notes, as well as one of your mastery questions in your tutorial. Okay, so stay with me. Increasing and decreasing functions are just O-level knowledge. In the O-levels, we have learned that if f prime x is more than 0, that means your dy dx is more than 0, then f will be strictly increasing. And if it is less than 0, then f is strictly decreasing. So that their graphs are going to look something like this versus something like this. All right. What is new in this section is the idea that it must be true for all x within the domain of f. So the domain matters. You may be wondering, why are we revisiting all this O-level stuff? The key thing here is about one-to-one functions. Now, functions which are strictly increasing or strictly decreasing are necessarily one-to-one functions because they will definitely pass our horizontal line test. Let us now consider an example. We want to show that this function f is strictly decreasing. So this is f. Let me use my GC to sketch it. Okay, enter. And I will use zoom standard as a starting point. Oh,
How is this a strictly decreasing function?
wait, the question says x is more than 0. So we should only take the right half of this graph. This then is our y equal to fx graph. In fact, it has a horizontal asymptote, y equal to 1. Now you can see that it's clearly a decreasing function. Okay, sliding downwards. Or more precisely, if we take any 2 points on the graph, let's call this a comma f of a. Okay, remember it's y equal to fx. And b, f of b. And because it is decreasing, we see that, let me write it this way, b is more than a, okay, will imply that f of b is less than f of a. This means that although b is to the right of a, but f of b will be below f of a, which fits the definition of a decreasing function. All right, but we have to note that it is not sufficient to just sketch the graph to conclude that f is strictly decreasing. We have to use differentiation. Okay, so when you differentiate fx to get f prime x, you find that you get negative 2 over x cubed. And this is where the domain comes in. Please change this to for all, right, to fit the description above. Now the domain of x is more than of f is x is more than 0. Okay, so for all x is more than 0, x cubed will be positive, and negative 2 over x cubed will be negative. Alright, therefore f prime x is negative for all x inside the domain of f. You may realize that in our explanation, we included this word continuous. And we might ask, what is continuous and why is it important? Alright, so to illustrate, I'm going to show you a graph which is non-continuous. Over here, I have copied the graph on the right just now. Let me scroll up. And let me add another part to it. Alright, so again, this kind of graph is familiar to us from graphing techniques. We see that between the left half and the right half, maybe let's say between here and there, there's no way that you can move along the graph from this point here below to the point there on top. So that's what is meant by discontinuous, right? It is disconnected. So I'm going to label this as f is not continuous and the previous one as f is continuous. What happens now when we take points like before, but from the different parts of the graph? We see over here that b is more than a, but f of b is more than f of a. So even though f prime x is negative for all x inside this domain here, because you can see that no matter what point we pick along the curves, it will be negative in terms of gradient. So even though f prime x is less than 0 for all x, f is not a decreasing function. Okay, as you can see, what happens when we move from the left half to the right half of the graph. So that should give you a better appreciation of the continuity requirement. But as always, please draw your graph first, and then you will know what to do. Let us turn the page and look at something else. Strange things can happen with functions that are non-continuous, and things are about to get stranger when we come to piecewise functions. They have a separate rule for each part of their domain. And do take note of their respective endpoints. So because it comes in pieces like this, it is called a piecewise function.
Surely such weird functions have no real-life application.
Consider the fare structure in Singapore for students. Okay, these are the MRT fares for students like you. Okay, up to 3.2 kilometer, right? The card fare per ride is 42 cents. Wow, that's really cheap. Okay, for the next extra kilometer is 47 cents, and then 52 cents, and so on. Okay, you may think that oh, it just follows an AP, right? But it doesn't. Notice that from the fifth term, it's no longer plus 5 cents. Okay, it's plus 3 cents. All right, so don't forget to check whether a sequence is an AP. We cannot just check the first 3 terms. We have to look at it in general. Alright, so this function here comes in 6 pieces, like a 6-piece KFC meal. How can we key this into our GC? One way is simply to key in y1, y2 all the way until y6 for them. But that is not the most efficient way. There is in fact a better way. If you go to math, press the up arrow, you can see somewhere at the bottom there's a piecewise option. So let's enter. How many pieces do we have? We have 6. Unfortunately, the GC can only give us up to 5 pieces. So now since we have 6 pieces, one way is to split it into 2 times 3. Right, so move down and choose OK. So y1, I will put in 3 pieces. The first rule is 42. Okay, 42. And then now we need to key in the subdomain here. Okay, this will be between 0 to 3.2. Okay, go to second math, which is test. Test contains all our inequality signs. Okay, so we want option 6, 0 less than or equal to x less than or equal to 3.2. Okay, use your right arrow to move to the next row. So this is 47. Okay, for x between 3.3 to 4.2. All right, so after we completed the first 3 pieces, we can check one more time that we keyed in correctly. Okay, press enter. So now we need to key in the next 3 pieces too. I will use Y4 because I prefer pink. And the last row is 63 cents for anything that is above 7.2 kilometers. Okay, done. What should we set for our window for the graph? We want our x value to be from 0 onwards. Okay, the distance can be 0 if you enter and exit at the same station. Okay, so anything from 0 to, let's say, 10. All right, for the y values, we want this range between 42 to 63. Okay, so I might draw, let's say, between 30 to 70. So I'll set my window accordingly, 0 to 10 for x and 30 to 70 for y. Let's press graph. Okay, so this is how the graph looks like.
Gosh, it looks like the staircase I climb at my block.
Yeah, this is a step function. Okay, step function. It is a typical example of a piecemeal function.
You mean piecewise?
Yeah, piecewise. Next up in our list of strange, special functions are periodic functions. In terms of fame, one of our most famous periodic functions are our trigonometric functions, our sine, cosine, and tangent functions. All right, these are all periodic in the sense that they will repeat themselves after a while. In fact, for sine and cosine, the periods are 2 pi. Okay, and for tangent, the period is pi, as you might recall from O-level math. So let's go back to our notes. And consider the graph of a periodic function, okay, like the one over here. This function is defined like this: fx equal to x squared plus 3 when x is between 0 to 1. Right, so this is the piece of the quadratic curve corresponding to x squared plus 3 between 0 to 1 for x. So that gives us the original or the first piece of the graph. Now let's look at this extra line here. Fx equal to f of x plus 1. What this tells us is that f of 1 will be equal to f of 2. And since f of 1 equal to f of 2 and f of 1 is equal to 4, that means that f of 2 will also be equal to 4. In fact, f of 0.1 will be equal to f of 1.1, f of 0.4 will be equal to f of 1.4, and so on. So this entire stretch will be replicated to its right by this equation fx equal to f of x plus 1. Does it work in the reverse direction too? Yes, it does. If I minus 1 from 0.1, I'll get f of negative 0.9. Okay, so this equation still follows the form of fx equal to f of x plus 1. And take note that it is true for all real numbers x. So this is okay. Similarly, if we move to the left, this will be f of negative 0.6. So in fact, we can keep moving to the left as well as to the right, because the domain for this function here is all real numbers. Therefore, this original copy, the yellow one, will replicate itself indefinitely to the right and to the left. That's a good question. If you consider this domain on which f is defined, you can see that this domain is of size 1. All right, so I say that this interval is of size 1 unit. Now, fx equal to f of x plus 1. The difference is also 1 unit. This difference between x and x plus 1 actually give rise to what we call the period of the function. So the period is also 1 unit. Therefore, there would not be any overlap. So it will be just nice. We shall now look at an example together. Here we have a function that is clearly piecewise, and it is also periodic, as seen from this equation, fx equal to fx plus 4. This means that the period of f is 4 units. What about the size of its domain? Now, because f is piecewise, it has two subdomains, 0 to 2 and 2 to 4. Overall, the size of its domain is also 4 units, right? Because 0 to 4, so it's 4 units. Once again, we see that these two are a perfect match. So we can be sure that they will not overlap when we join the pieces together. To practice your GC skills, you may want to key in this using the piecewise function method, all right? So give it a try. Is this what you key into your GC? And when we press zoom standard, this is the graph we will get. Okay, so this is the original unit of the graph. We need to repeat this pattern because this is a periodic function. Okay, so this is our original piece of the function. When x equal to 0, when x equal to 2, right? 7 minus 2 square is equal to 3. So there's a point 2, 3 on the graph. When x equal to 4, 2 times 4 minus 1 is 7. So there's a point 4, 7 on the graph. What about when x equal to 0? You can see that over here, 0 is excluded. But supposing we sub in 0 into x, we find that we get 7 minus 0 square, which is 7. So this point right now is being excluded. But let us notice something. This periodic function here, this equation tells us that f of 0 is equal to f of 0 plus 4. Therefore, f of 0 should be equal to f of 4. Indeed, I want you to be aware that when we sub in x equal to 4 into 2x minus 1, we will also get 7 as the output. So that's why these two extreme endpoints have the same height and they will join together nicely in a repeating pattern. And because of that, there's now no need to exclude this point, all right? As they overlap, this point will also be included. So let us now proceed to clone copies of this graph between x equal to -7 to x equal to 10 inclusive. We have now reached the two ends of the graph at x equal to -7 as well as x equal to 10. But what are the y ordinates at those points? First off, does it make sense to sub in x equal to 10 into either of these equations? If we try to do that, we'll find that 7 minus 10 squared will be -93, and 2 times 10 minus 1 will be 19. Look at this graph. Can either -93 or 19 be the y coordinate of this point?
That's ridiculous.
Yeah, that's right. It is ridiculous to do that. What then is the correct method? We need to realize that 10 minus 4 is 6. So this point here, our endpoint, is actually corresponding to this point over here, where x is 6, and which itself is a clone of the point at which x is equal to 2. And since it is a clone, it means that the y coordinate, the y ordinate, okay, of this point here would be actually the same as that of its original, which is 3. Similarly, this point at which x is equal to -7 would correspond to the point at which x is -3. Okay, you plus 4 to it, and which itself is a clone of the point where x equal to 1. Now, x equal to 1 falls within this subdomain. So when x equal to 1, we get y equal to 7 minus 1 square, which is y equal to 6. Therefore, this point is 3, 6. And we can deduce that the left endpoint is actually -7, 6. Phew. Do we have to label all the turning points or the sharp points as well? The answer is no. Usually what you can do is just label the important points on the original copy, okay, between 0 to 4 in this case. of the graph, and then just label the endpoints. That will do. Of course, do not forget to label the graph as y equal to fx. So that was part 1 of the question, and part 2 actually uses the same idea. F of 27 plus f of 45. We do not simply substitute in 27 or 45 into these equations because that will not work. Instead, we see that f of 27 is actually equal to f of 23, right? By virtue of the equation here, equal to f of 19 and so on. And similarly for f of 45. So where does all this lead to? To the GC, of course. Did you know that your GC has a quick way to find the remainder? Press Math. Go to the right under Number, press Up, and you can see option 0 is the remainder command. Select that, and we can key in the dividend, okay, the number to be divided. Put a comma in between that and its divisor. Close the bracket. Voila! That is the remainder when 27 is divided by 4. Let's do it one more time. I'm going to copy and paste this and replace the 27 by 45. So that has remainder 1. So f of 27 is actually equal to f of 3, and f of 45 is equal to f of 1. Since 3 lies in the second subdomain, whereas 1 lies in the first subdomain, we just apply the respective rules. Actually, we have found them earlier, but I'll just do it one more time. Okay, so for f of 3, it will be equal to 2 times 3 minus 1. For f of 1, it will be 7 minus 1 square. We press our calculator and we get the answer 11. As promised, I have shared with you some useful GC keystrokes. Remember to apply them. Now, we are going to look at a self-reading example as a bonus on how to recover an individual function from a composite function. Let us turn to example 17. In this example, we are given the rule for hx as well as ghx and asked to recover or to uncover what is gx. So look at the working. If you see the first method, one way is to make x squared plus 2 appear somewhere in our equation. That means we force it to appear. This is not often easy to do, all right? You can see here, GHX is a quartic polynomial. So in the solution, we completed the square and then rewrote x squared minus 1 as x squared plus 2 minus 3. Okay, so while we worked here, this method is not easy in general. Even the alternative method might make you wonder, what's going on? And many of you might be scratching your heads here. Since these are polynomials, let me write down the alternative method in another way. In this way, you will realize that this is actually a form of long division. So after you do your long division, you get your quotient and remainder. We proceed to rewrite our quotient such that x squared plus 2 will also appear here. So now can you see that x squared plus 2 appears 3 times in this equation? And all that is left to do is to replace x squared plus 2 with x, so that in general g of x will be equal to x minus 6 times x plus 13, which is of course equal to x squared minus 6x plus 13. If you don't mind longer but more systematic approaches to a question, then this method of using long division might work well for you. At this point, some of you might be wondering, what if we were given hgx equal to x4 minus 2x squared plus 5 instead? Can we also find gx? Let's try it. Now we have h of gx is equal to x4 minus 2x squared plus 5, and h of anything sends it to is square plus 2. Therefore, we have gx whole square plus 2 equal to x4 minus 2x squared plus 5. So we can see that gx is simply plus minus square root of x4 minus 2x squared plus 3. And as usual, we will reject the wrong one, okay? Based on the range of g. Right, so this seems not so difficult compared to the original question. You may like to spend some time to review this example again, as well as the version I gave, okay, to recognize where the difficulty lies in such questions. And now I'm going to move on to a tutorial question, mastery question number 13. Part 1 of this question is actually quite straightforward if you recognize that f squared x is just f of fx. It is part 2 that intrigues us because for 1 mark, we are asked to find f3x in simplified form. No kidding, 1 mark to find f3x. And that is because part 2 depends on part 1. If you understand part 1, it is saying that taking 2 steps forward, ff, is the same as taking 1 step backward, f inverse. How can we represent this in a diagram? It will look something like this.
Oh, so you're saying the function can loop back on itself?
Yeah, like forming a cycle. So if we continue in the clockwise direction, apply f a third time, can you see that? We will end up back at x. So f3x is just x. If you want to show some working, it will be like this. And f of f2x is simply f3x. Whereas f of f inverse x, just back and forth, we will get x. Okay, that concludes our entire series on functions. We hope that HBL will be over soon, and we'll see each other again. Bye.